Good day. Today we will discuss our 5 problem in calculus. Number 1. Consider a tank that is leaking water. Assume that the tank is with the shape of an inverted right cone. The dimension of the conical tank are a height of 16 feet and a radius of 5 feet. How fast does the depth of the water change when the water is 10 feet high? If the cone leaks water at a rate of 10 cubic feet per minute, we need to find the derivative of h with respect to t, given that h is 10 and dv over dt is negative 10. The volume of a cone is equal to 1/3 pi r squared times the height. Since there are 3 variables in the equation, let's try to reduce it by expressing r in terms of h. First, observe that the ratio between the radius and height is constant throughout the cone. So we can say that r over h is equal to 5 over 16. Then r is equal to 5h over 16. By substitution, we get a new equation. To find th over dt, we take the derivative of both sides. dv over dt equal 25 pi over 256 times h squared dh over dt. Substituting the given, we get dh over dp equal negative 0.33 feet per minute. Number 2. A 6 feet tall person walk away from a 10 feet lamppost at a constant rate of 3 feet per second. What is the rate the tip of the shadow moves away from the pole when the person is 10 feet away from the pole? Let d be the distance between the person and the lamppost, s be the length of the shadow, and x be the distance between the tip of the shadow from the pole. That is, x is equal to d plus s. We need to find dx over dt when d is 10. Using the illustration, we can extract 2 similar triangles with base t plus s and s. Then we can form a proportion from the ratios of their base and height. d plus s over 10 is equal to s over 6. Through some algebraic manipulation, we can express s as 3/2 d. Now we can write x in terms of d. X is equal to d plus 3/2 d, then x is equal to 5/2 b. Differentiating the equation, we get dx over dt equals 5/2 dd over dt. Simplify and we get 15.5 feet per second as the final answer. Number 3. A 10-foot ladder is leaning against a wall. If the top of the ladder slide down the wall at the rate of 2 feet per second, how fast is the bottom moving along the ground when the bottom of the ladder is 5 feet from the wall? First, we need to find an equation that includes x and y. Observe that the ladder forms a right triangle with the wall and the ground. That being said, we can use the Pythagorean theorem. X squared plus y squared is equal to 10 squared. Given that x is 5, we can now find y. After that, we take the derivatives of both sides of the equation. We get 2x times dx over dt plus 2y times dy over dt equals 0. Recall that we are trying to find dx over dt, so let's only leave dx over dt on the left side. By substituting the given, we get 2 square root of 3 feet per second.
A cylindrical container with circular base is to hold 64 cubic inches. Find its dimensions so that the amount of metal required is a minimum when the container is a closed can. Before we proceed with the solution, let's first try to analyze the given and what we have to find. The container holds 64 cubic inches. Then it is the volume. We need to find its dimensions so that the amount of metal, the surface area in other words, is minimum. And we can only say that the surface area is at minimum when its derivative is equal to 0. The volume of a cylinder is equal to pi r squared times height. The surface area is equal to 2 pi r squared plus 2 pi rh. It would be easier if we express the surface area in terms of only one variable. So, let's try to express each in terms of R. Given that the volume is 64 cubic inches, we can substitute it to the volume formula and get H in terms of R. H equals 64 over pi r squared. Now, replace H. Surface area equals 2 pi r squared plus 2 pi r times quantity 64 over pi r squared. Simplify the equation to its exponential form for more convenient differentiation. Now, SA prime equals 4 pi r minus 128 r to the power of negative 2. Since the surface area is at minimum, its derivative is equal to 0. From here, we get r equals 2.17 inches. Next, let's use the derived formula for height. Substitute the calculated radius. We get h equals 4.34 inches. To sum up, the amount of metal required in a closed can is at minimum when the radius is about 2.17 inches and the height is about 4.34 inches. Consider f of x is equal to x squared plus x plus 1. Determine a. the intervals where f is increasing or decreasing. B. the local minima and maxima of f. C. the intervals where f is concave up and concave down. And D. the inflection points of f. Option E. We can start with sketching the graph of the given function to visualize the problem better. Given a quadratic function in the form of ax squared plus bx plus c, the vertex can be found at the point negative b over 2a and f of negative b over 2a. A is 1 and b is 1, so the vertex is at the point negative 1 over 2 and 3 over 4. From this single piece of information, we then conclude that the function is increasing between negative 1 over 2 and the positive infinity, while the function is decreasing between the negative infinity and negative 1 over 2. Since the graph of the function is an upward parabola, the local minimum is the vertex itself, while there is no local maximum. This also implies that the function is concave up throughout the graph, and there is no such interval where the function is concave down. Now, to find the inflection points of the function, we perform the second derivative test. The first derivative is 2x plus 1, and then the second derivative is 2. Therefore, as the second derivative is constantly positive, the graph has no inflection points. Merry Christmas, sir. Happy holidays. Congratulations on your new baby.